In this section, we're going to continue to look at series, but we're going to basically put some more tools in our tool belt in terms of deciding whether a given series is convergent or divergent. So in the last section, we learned about geometric series, right? And so with the geometric series, we're talking about ones that look like this. And we said that they're convergent if the absolute value of r, right? If the absolute value of r is less than 1. And then they specifically converged this number. This is going to be their sum. Okay, and so that was great. And then we also introduced the test for divergence, which was just a test that said if the terms don't go to 0, then there's no way the series can converge. And that's what we learned in the last section. This is a very specialized series, right? And so we want to kind of expand the types of series we have the ability to evaluate. So to start, we're going to do something that doesn't look like a series at all. In fact, what I'd like you to do is, pause the video and try to do this problem. This is a problem you would have done back in Calc 2 just last quarter. It's an improper integral. But what I want you to answer for me is, can you figure out what values of p are going to make this integral convergent? So pause the video, take some time to work on that, and then we'll come back together and make sure that our solutions are the same. All right, so remember that when you're working with improper integrals, the whole key here is to understand that you cannot plug infinity in to an antiderivative, right? Infinity is not an actual number. So remember with these, we kind of cheat a little bit. We say the integral from 1 to infinity of 1 over x to the p dx, we're going to say is going to be the limit as t goes to infinity of the integral from 1 to t of this. And so it kind of seems like, okay, really, have we changed anything fundamentally? And the answer is yes and no, right? We're still, letting t go to infinity, so we're still calculating the same integral, but t is something that I can comfortably plug into any antiderivative. All right, so remember what we're doing here is we're getting it ready to have its antiderivative taken. And so this will be from 1 to t x to the negative p dx. And so now I'm ready to take the antiderivative, right? So what do? We add 1 to the exponent and then divide by that new exponent when we take an antiderivative. And we do that from 1 up to t. All right, so this gives me the limit as t goes to infinity of t to the negative p plus 1 divided by negative p plus 1 minus 1 to the negative p plus 1 over negative p plus 1. All right, so we have this mess here. So what we got to do is we got to, make some sense of this. Now, I suppose that there's a number of ways that we could try to simplify this, but here's the way I'm going to do it. Your work does not have to look like this. On the one hand, this negative p plus 1 is just distracting. Let's remember that p is an actual number, right? And so this is just a number in the denominator, and it doesn't have any t's in it at all. So I'm going to pull that outside. Okay, pull that outside the limit. And then the other thing that I'm going to do to make this just a little bit more palatable is I'm going to turn the t to the negative p plus 1 into t to the negative p times t to the 1. All right, we know that when you multiply like bases, you just end up adding the exponents. And then we have our 1 over here, but guess what? 1 doesn't really care what we raise it to, right? It's still just 1. And so lastly here, what I would say is this is 1 over negative p plus 1, and the limit as t goes to infinity, and this is t divided by t to the p, right? Because we bring the t to the negative p down and make the exponent positive. Now, the whole question here is, would you agree, is that uh, if this p here is bigger or smaller than 1, right? Because if p is larger than 1, then that means that the limit is going to equal, that the limit is going to equal, I guess, -1 over negative p plus 1. But the important part is that this thing goes to 0 here, right? So we'll just make this comment. If p is greater than 1, then the limit exists, right? And so we have a convergent improper integral, right? And that's just because if p is greater than 1, then the bottom basically wins out over the top, right? If p is less than 1, then that means the top wins out and t goes to infinity, so that means the limit does not exist. Right? And so it is divergent. Okay. And now what I started with here actually was slightly off. And what I mean by that is this is clearly what's happening when p is greater than 1 and when p is less than 1. But let's understand that if p was 1 to begin with, then we actually have to recompute the whole integral, right? So if p equals 1, then what we would have had was the limit from t to infinity of the integral from 1 to t of 1 over x dx. And let's understand that when you have 1 over x and you take its antiderivative, remember what we get is the natural log, right? So we don't get anything that looks like this at all. We get the natural log. So this would be the natural log of x from 1 to t. And sorry, I forgot my limit. Shame on me. Okay. And so this is going to equal the limit as t goes to infinity of the natural log of t minus the natural log of 1. But let's remember that when you take the natural log of t and you let t go to infinity, even though the natural log is a very slow growing, I want to fix this here, it's a very slow growing function, it's still growing forever nonetheless. And so what we know is that this limit does not exist. And so that means it's divergent. So what we can do to summarize all of this work we've done, put it in this box here, is we can say that it's convergent if p is greater than 1, okay? And divergent otherwise. All right. Now, let's look at something very similar, right? But instead of looking at the integral, which you've done before, let's take a look at the series, okay? The series, 1 over n to the p, right? As opposed to the integral 1 over of 1 over x to the p, okay? And so it says it turns out that the same exact values of p make the series convergent as made the improper integral convergent. Okay, and I'm asking you to make an argument for this. And let me actually get your argument started here. I don't want you to give me a proof, but here's what I want you to think about for a moment. Let's make a little graph here. Actually, two graphs. Okay. And let's sketch what we know would be a convergent situation in terms of an integral. Okay, 1 over x squared. All right, so what I'm going to do here is I'm going to make a couple of notches. So here's 1, 2, 3, 4. That's probably good enough. And then I'm going to let 1 be actually way up here. Okay, so I know when I put 1 in for x, y is 1. When I put 2 in for x, y is a quarter, right? So here's a half, here's a quarter. So here, and then when it's 3, it's a ninth. So that's, pretty far down there. Then a 16th, so that's also pretty far down there. And so here's what we have. Starting, and I'm just going to graph it starting at 1 here. I know that this function, if I integrate it from 1 to infinity, is convergent. Okay? All right. Now I'm going to leave that there for a second. Now I'm going to draw one more picture, and it's going to be of something that I know is divergent. Okay? So in the last in all our work here, when p was equal to 1, it was divergent, right? So I'm going to go ahead and sketch, in this, instead of 1 over x squared, I'm going to sketch 1 over x this time. All right, so here's a 1, 2, 3, 4. Put 1 about the same spot. All right, so now I'm trying to get a handle on this 1 over x dx. So got a point there. When x is 2, y is a half. When x is 3, y is a third. So that puts me up there. Then it's a fourth. All right, so now if I'm integrating from 1 to infinity, I'm trying to integrate this, right? Okay, and let's use a different color since it's divergent, right? That sounds bad, so let's make that red. So I know that this red area under the curve is actually infinite, right? This is a divergent situation. Okay, so infinite area here, a finite area there. So here's what I want you to do. I want you to take a moment, pause the video, and think about how the series might be able to geometrically relate to these pictures that I've already drawn here. And so just think about this 1 over n to the p, right? So for example, down here, maybe let's think of n equals, let's not use red. Sorry, let me get a neutral color going here. So down here, let's think about n equals 1 to infinity of 1 over n squared, right? So what's that going to be? That's going to be 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, and so on, right? Which is 1 plus a fourth plus a ninth plus a 16th, and so on. And then over here, by contrast, right, 1 plus a half plus a third plus a fourth, and so on. So here's my question. We already know, because they told us, that the same values of P make series convergent and divergent. So we know that this should be convergent, right? We know that the other one should be divergent. And so I want you to think about why that is geometrically. Okay? So how can you fit this idea into this picture? Okay, so take a few moments to think about that. If you think you have some good ideas, try them. If you have no idea what in the world I'm asking you, then I'm probably, maybe I'm asking it really poorly. But just take a minute to at least think about it a little bit before you see my solution. Okay, so I don't know if you thought of this or not, but what I want you to think about is that each of these numbers, okay, each of these numbers here, 1, 1/4, 1/9, 1/16, they could represent the area of a shape. The reason I think that might be nice is because we already have this expressed as an area, and we know that this area is finite. Now, how could we do that? Well, because all of these, each of these have width 1, then if we make the height of a rectangle here equivalent to these numbers here, then we get a nice geometric representation. So here's what I mean. I'm going to start with 1/4, okay? So 1/4 would just be a rectangle right here. And that has an area of 1/4. This one here, 1/9, okay? That area is 1/9. That little tiny area there is 1/16. Now, so I'm excluding the 1 here, but can we agree that the total areas of all these rectangles are going to be less than the total area in green? And since we know the total area in green is finite, that means the areas of all these little rectangles have to be finite. All right, and you say, well, you left one out, you left one out. Well, sure, I left one out, but just understand that if you have a finite total area here, then there's nothing wrong with adding one single rectangle with an area of 1. So that's how this idea of a series relates to this idea of the improper integral. All right, now here, how do we show this is divergent? Okay, we probably guess in just about the same way. But here, the way I'm drawing it is, I'm going to put my first rectangle here that represents my first term of 1. Then my second rectangle here that represents a half. My third rectangle here, which represents a third, and so on. And so here the idea is, if all these numbers represent the areas of these rectangles, and I know that the red area is infinite, then that must mean that this sum is also infinite and therefore is divergent. All right, so that was kind of a long time we spent on that. And it does kind of button up what we're saying here. This thing, 1 over n to the p, is known as a p series. It's convergent if p is greater than 1, and it's divergent if p is less than or equal to 1. All right, but this also gives us a more general idea, about how to evaluate series, whether they're convergent or divergent. All right, so we just related, back on this page, an integral to a series and allowed that to kind of inform us about the convergence or divergence of that series. All right, so what we can do is something called the integral test. And what it says is, if the terms of your series are represented by a continuous function that is positive and decreasing on the interval 1 to infinity, then you know that the series is convergent if and only if the improper integral is convergent. And if and only if just means it goes both directions. This being convergent means that is, that being convergent means that is. And then by extension, it also means divergence here equals divergence there, and the other way around. All right? So that's what these two things are saying. So can you essentially turn your series into the equivalent function integrated from usually 1, but it could be, I guess, another number up to infinity. All right, so let's put this idea into practice here. So here's a series. It is not a simple p-series, right? There's more going on than that. It's got an n squared in the bottom, but then it's got an n on top. It's got a +4 on bottom, so it's not a pure p-series. But here's what we can do. We can say, all right, let's think about the function f of x. And let's see what happens to it when I integrate it from 1 to infinity. All right. Now, we know what to do here. We introduce this t and say the integral from 1 to t of x over x squared plus 4 dx, and we're going to let t go to infinity. All right. All right, so now let's review some integration techniques, right? So take a moment to think to yourself, how do I actually execute this integral? And if you take a few moments to do that, hopefully pausing my video to do so, hopefully you recognize this idea that the derivative of the bottom is looking a heck of a lot like the top. And anytime that happens, it's worth trying use substitution, right? So this is where we would say, let's try to put x squared plus 4 as our u. And then that means that du dx would be 2x. So du equals 2x dx. And then there's different techniques you can use, but I kind of like to just get dx all by itself. I think that's the way that students tend to like to look at it. Oops. So du over 2x is dx. And so we can do those substitutions. Of course, please don't forget about changing your limits of integration, right? That can be a place where use substitution can bite us. So this will be the limit as t goes to infinity. All right. Now, if u is x squared plus 4, then remember to change these limits of integration, I need to plug these numbers in for u. So I plug a 1 in for x, so 1 squared plus 4 is 5. So my new limit of integration on bottom is u equals 5. And on top, it's u equals t squared plus 4, right? Just plugging directly in here. And then here we have x over u, because x squared plus 4 became u, and then dx became du over 2x. So my x's cancel. There we go. And then we can, of course, pull our 2 out in front. Sorry, I'm having trouble here. There we go. And so this whole thing becomes the limit as t goes to infinity of 1/2 okay, and then this should resemble one of the cases we were working out on that first example, right? The antiderivative of this is the natural log. So this is the limit as t goes to infinity of 1/2, and then it's the natural log of u from 5 up to t squared plus 4. Now, almost there, but hopefully you can kind of see where we're going here. So this is the natural log of t squared plus 4 minus 1/2 times the natural log of 5. But the important part is, what happens to this term as t goes to infinity? The answer is it blows up, right? This thing blows up. And so this, since this does not exist, this limit does not exist, so that means that the integral and by the integral test, and therefore our series is divergent. Now, one of the things before we move on from this example that I hope you can kind of look at, let's just agree for a second here that when you look at something like n over n squared plus 4, the plus 4 is just not that important in the grand scheme of things, right? In terms of how big these terms are actually getting, the 4, it just doesn't matter all that much. So this is a lot like, not exactly, but it's a lot like n over n squared, which would be 1 over n. And if it was 1 over n, we would immediately see that it's a p-series, right, that has to diverge. So one of the things I want you to do is, before you just dive headlong into the formal tests and things like that, is to just kind of get some intuition and say, what do I think is going to happen to this thing? Sometimes that intuition can be wrong, but more often than not, it's going to be right. And it's always good to have that in your back pocket, so that way you know if maybe you've made a mistake along the way that gave you the wrong answer. All right, here's another example. So that last one was divergent. Let's see if we get divergence here as well. So we want to determine if this series is convergent, right? So we'll consider f of x is equal to this. So that's the function we're going to work with. We're going to integrate from 2 to infinity of 1 over x times the natural log of x squared dx. All right, so now let's think about what do we do here. So in the last problem, we did use u substitution, right? And when we use u substitution, our rationale was that if we substituted out the x squared plus 4, the derivative of that is going to look a lot like the other part, and then we might get some nice cancellation. All right, so let's take a look here. We have the natural log of x. What's its derivative? Well, its derivative is 1 over x. So I'm feeling like it's pretty promising to let my natural log of x be my u here. All right, so first of all, let's, before I get too far ahead of things, let's express our improper integral in a more proper fashion. All right, and so let's make that substitution, right? So u might equal the natural log of x. Then in that case, du dx is equal to 1 over x. So that means, doing a little cross multiplying there, x times du is my dx. So this would be the integral, and remember, we're making our substitution, so it's the u equals the natural log of 2 and the natural log of t here. And then this is going to be 1 over x times u squared and then x du. And we get that nice cancellation we were hoping for. All the x's are gone. All I see are u's now. And then in this case, when you have a u squared on the bottom, right, that's when we're just going to use our power rule of antiderivatives. So we've got integral natural log 2, natural log t, u to the negative 2 du, which is going to be the limit as t goes to infinity of, so it would be u to the negative 1 divided by negative 1 evaluated from the natural log 2 up to the natural log of t. So the limit as t goes to infinity, so I'm plugging in natural log of t. Actually, let me do this first, 1 over u, natural log 2, natural log t. So the limit as t goes to infinity of negative 1 over the natural log of t, and then minus negative, so plus 1 over the natural log of 2. But the important part here is what happens when t goes to infinity. As t goes to infinity, this number on bottom gets larger and larger and larger, which means this entire term goes to 0. So that means that the limit exists and equals 1 over the natural log of 2. So we can say that since the integral is convergent, so is the series. All right. So now let's take a look at another one here. So I've got the series of adding up from 1 to infinity, 1 over n squared plus 4. Okay. Now, this problem, I absolutely could do the integral test, right? So I could do f of x is equal to 1 over x squared plus 4. And I could integrate from 1 to infinity of 1 over x squared plus 4. And then I could definitely pull out my table of integrals. And I'm going to skip a few steps here and not show everything. But I'm just going to kind of cut to the chase, because the point of this example is not to do the integral test again, but to show an alternative way that we could do this problem. But what I would do is, you might remember what to do with this. You can do some fancy u substitution and maybe remember that this kind of resembles the derivative for the tan inverse, but that might be a little tougher one to remember. So we'll just say this, table of integrals in the back of your book, and I'll even be specific here, table of integrals number 17. That's going to tell you that this is the limit as t goes to infinity, and it is 1/4 times the tangent inverse of x over 4, and of course evaluated from 1 to t. And I'm not going to go through all the, but just understand that when you plug t in here and let it go to infinity, the tan inverse approaches pi over 2 as its argument goes to infinity. So basically from this you'll see it's convergent. Okay, but the point of this problem is not to go through and do all of that. The point is to say that's a lot of work, right? And it requires a bunch of knowledge. It requires some knowledge of the tangent inverse function. It requires going to the table of integrals. So what the point is, lots of work. Okay. So let's look at this here. 1 over n squared plus 4. It sure looks a lot like a simple p-series. It's just that plus 4 that's bugging us. Now I want you to think back to our work with sequences for a moment. is there anything from our work with sequences when we were trying to determine convergence and divergence that might help us here? Maybe pause it for a moment and think about that. When we worked with sequences, what we knew was that we could use the squeeze theorem to simplify to simplify our thinking. And if we could figure out that a particular sequence that was simpler converged, and we could put our sequence between two simpler ones that converged, then we knew that ours converged to the same thing, right? We can do the same thing here. So in general, it's definitely always true that this is always smaller than this, right? The more you have in the bottom of a fraction, the smaller the number is, okay? And on the other hand, we definitely know that these are always, right? Always greater than or equal to 0, okay? So what we can do is essentially compare. And so the logic goes like this, right? We know this is convergent. Oops. Is convergent since it is a p-series with p greater than 1. But we also know that every single one of these terms is going to be smaller than its counterpart over here. So if adding up all these terms gives you a convergent series, then adding up a bunch of smaller terms has to also give you a convergent series, when especially when they're all positive, right? So we know that. So therefore, n equals 1 to infinity of 1 over x squared plus 4 is convergent. And so what are we basing that off of? We're basing that on comparing two different series. So we'll say it's convergent by what we call the comparison test. All right, so what does the comparison test say formally? It says, suppose that you have two series where all the terms are positive, then if the series B sub n is convergent and all the terms in A sub n are smaller than or equal to all the terms in B sub n, then A sub n is also convergent. On the other hand, if this guy is divergent and all the terms in your series are bigger than or equal to all the terms in that divergent series, then yours must be divergent. So we just did a comparison test to show convergence, okay? Let's take a look at this one here. All right, so again, this is kind of complicated. The secant of n, right, in absolute values, less and square root of n. Well, can we say anything about it? Can we compare it to a different series that might be easier to get a hold of? Well, what do we know about secant? Okay, we know that secant is 1 over the sine, right? So the secant of x is 1 over, did I say sine? Excuse me, it's 1 over the cosine. So the secant is 1 over the cosine. So the cosine is always between -1 and 1. So what that means is that the reciprocal of cosine is always bigger than 1 or smaller than -1. And if we go back to your trig knowledge here, remember that secant looks like this, right? Got some vertical asymptotes there, right? That's what your secant graph is going to look like. But the important part about it is this is a -1 and that is at 1. So it never is between -1 and 1. So what we can say is that the absolute value of the secant is always greater than or equal to 1 over the square root of n. So it looks like we're setting this up to do this kind of comparison. So is this series divergent? Well, yes, it is, because remember, the square root of n is the same as n to the 1/2. So we can say that that is divergent because it is a p-series with p less than 1. And then we can further say then that by the comparison test, our series is also divergent. Okay. Now what I want us to do here is think about an example that is related to the example we did 2 times ago, which was 1 over n squared plus 4. Okay, so I'm just going to write over here. Let's just remind ourselves that this 1 over n squared plus 4 converged, right? So if I look at this series compared to that, they don't really look all that different to me, right? One has plus 4, one has minus 1. But the thing that allowed us to use the comparison test here was the fact that when you're adding something to the denominator, that's always going to be smaller than or equal to than if that addition wasn't there, right? So our comparison back in this problem was to compare these and say this is smaller than or equal to that. So to use the comparison test to show that this converges, we would have to be able to say that it is smaller than or equal to some simple thing like a p-series. But the truth is 1 over n squared minus 1 is always going to be greater than 1 over n squared because you're taking away from the denominator. You're taking away from what you're dividing by. So even though we are probably 100% certain that if this converges, this has to also, the comparison test can't get us there. So an alternative, which is really superior to the comparison test because you can use it a lot of the times you would have used the comparison test anyway, is to use the limit comparison test. And so the idea is this. If you have 2 series and you take the limit of their terms, the limit of the ratio of their terms, if that limit is a finite number, then either both series have to converge or both series have to diverge. And here's what this is saying. If we're taking the limit of the terms of the sequence, of the ratio of terms, what we're doing is really we're comparing the speeds with which these terms are heading towards 0. So if 2 different series have terms that are kind of going to 0 at the same speed, then they should kind of balance each other out and give us a finite non-zero number here. If the bottom is dominating and going to 0 much faster than the top, that's when you get 0 here. If the top is dominating and going to the bottom, or going to 0 much faster than the bottom, then that's when you get infinity here. And then you can't really say anything about it. But if you know they're going to 0 at about the same speed, then either they're both converging or both diverging. So just think of it, it's all about how fast you're getting to 0. So this one, while I couldn't use just the pure comparison test to compare it to 1 over n squared, what I can do is use the limit comparison test. So I can say that I'm going to take 1 over n squared minus 1 divided by 1 over n squared, which is 1 over n squared minus 1 times the reciprocal of the denominator. So the limit then goes to infinity of n squared over n squared minus 1. And of course, we've played this game a couple of times, right? The whole goal is so that we have a constant term on the bottom without any variable in it, and where everything else has the variable in the denominator. So I'm going to multiply both the top and bottom of this by 1 over n squared. So we have the limit as n goes to infinity of 1 over 1 minus 1 over n squared, which is equal to 1. So that means either both converge or both diverge. And we know the series of these terms always converges because it's a p-series. So we can say since this is convergent, because we got a nice finite non-zero number here, n equals 1 to infinity of 1 over n squared minus 1 is convergent by the limit comparison test. All right. So the last topic here for this admittedly long lesson is to actually start to get some idea of what the sum of a series actually is. We, with our geometric series in the last section, we actually were able to write down what they added to, and we haven't even addressed that. Every single example we've done has just been about, does it converge, does it diverge? That's the only question we've answered. So to answer that question of, okay, well, what do we do to figure that out? At this point, we're just left with start adding up terms. And generally, that's going to be what you're going to do. You're just going to add up terms for a while. But then, of course, you understand that if you're just going to add up a certain number of terms, you've got to stop at some point. And if you stop at some point, it's not going to be perfectly accurate because you've left some stuff out. So we want to get an idea of, if I add up, like, say, the first 20 terms of a series that converges, how big is the remainder? How big is the leftover? Okay, so that gives us a definition here. So the remainder is the error when you use a partial sum, right? So when you use a partial sum, so remember, a partial sum would be a1 plus a2 plus all the way up to an. When you use a partial sum, the remainder is the difference between that partial sum and the true sum, right? That we're calling S, the true sum. And what is that? That's just going to be all the remaining terms that you never got around to adding. All right, so what would be nice is if we had some idea of how big that remainder was at any given point, right? How inaccurate are we if we add up the first n terms? So here's the remainder estimate for the integral test. It says, suppose that you have a function, again, that is kind of representing the formula for the terms of your series. And f is continuous, it's positive and decreasing. Okay, for at least for all x's bigger than or equal to the n that you stopped adding at. Then the remainder has got to be between these two integrals. Okay, the remainder will always be between these two integrals. Okay, well, let's think about why that is. So the remainder that's left over has got to be bigger than integrating from n plus 1 up to infinity. Okay, and the reason you can see right here. Okay, because if you're starting the integration at n plus 1, that's going to give you all this, right? But a rectangle that goes up to this particular height to represent the term, an plus 1, and this represents an plus 2, they're going to go up to the height determined by this function, and then there's going to be some sticking up on top and sticking up on top. And so you know that your remainder is definitely going to be bigger than this integral. But on the other hand, if you started at n instead and integrated all that, then the term a sub n plus 1, its right side would go up to and hit the function, and so then there would be this empty space here. So the integral, the area under the curve, would actually be bigger than summing up all these terms. And again, what are we doing? We're thinking of the area of each one of those rectangles as the value of that particular term in the series. All right, so that's why we can always say the remainder is stuck between there. And then if you just take this and add s sub n to each part of this inequality, then of course you get the s sub n here, you get the s sub n there, and then r sub n plus s sub n, well, this is the partial sum up to n, this is the remainder. If you put those together, that becomes the true sum. So that's another inequality that'll be useful to us. So this is saying the true sum is somewhere between the partial sum plus this integral and the partial sum plus that integral. All right, so that's a lot of notation there, but let's do a concrete example, I think, to help us out. So part A asks us to just add up the first 6 terms of this series. Okay, well, we can do that. So n equals 1 up to 6 of this. By the way, this is just the same, and I think we'll find it more helpful to do it like this, as 3 halves, right? Because remember that this always turns into the fraction exponent x to the m over n. So this is n to the 3 halves here. So this is 1 over 1 to the 3 halves plus 1 over 2 to the 3 halves plus 1 over 3 to the 3 halves, and so on. And that's just a matter of plugging into our calculator, and what I get there is approximately 1.828. All right, so now let's take a look at part B. So it says provide upper and lower bounds for your estimate from part A, right? So what's the smallest it could be? What's the biggest it could be? So remember, what we're doing here is we need to get an estimate on how big the remainder is, right? So that if I represent the formula for the terms in our series with a function and I integrate it from n plus 1 to infinity, that's going to be the lower limit of where our remainder is, and then the upper would be integrating from n to infinity. All right, so remember, for us, our partial sum was the 6th term, right? So that was 1.828. But the key is n equals 6 when it comes to applying this remainder theorem. So I need to integrate from 6 to infinity. And we're talking about the series 1 over n to the 3 halves, right? So that means I should be talking about the function 1 over x to the 3 halves. So that's the limit as t goes to infinity of the integral from 6 to t of 1 over x to the 3 halves dx, right? We know that we want to pull that x to the 3 halves up top. And so this will be the integral from 6 to t of x to the negative 3 halves dx. And then, of course, we are going to add 1 to our exponent. So this will be x to the negative 1/2 divided by negative 1/2 from 6 to t. So this, of course, can become negative 2 on top, right, dividing by negative 1/2. And then on bottom, x to the 1/2 from 6 to t, right? But that's going to be the limit as t goes to infinity of negative 2 over t to the 1/2, or the square root of t, plus 2 over the square root of 6. But if you take the limit as t goes to infinity, this term zeroes out, and so we just get 2 over the square root of 6. Now that was just the upper estimate for our remainder, right? The lower estimate is the integral from 7 to infinity. But luckily, if we just take a careful look at what we just did, the only place the 6 came into play ultimately is in the denominator of our answer. So we can confidently say this is 2 over the square root of 7. So what this means is that the remainder after 6 terms is somewhere bigger than 2 over root 7, but smaller smaller than 2 over root 6. And so then that also means then that the true sum is got to be between 1.828 plus 2 over root 7, the remainder, and the partial sum 1.828 and plus 2 root 6. And so if I plug that in the calculator, that means that the true sum, I don't know exactly what it is, but I know that it's somewhere between these two numbers. Right? So I've gotten within fairly close, right? Definitely within 0.1. We're accurate within 0.1 there. All right, so then the last question here then would be, can we make some sort of estimate about if I want a certain degree of accuracy, right? What do I do? Okay, so it says how many terms are required to ensure that the sum is accurate to within 0.0001. Okay, so in other words, we want to know what is n so that the remainder is smaller than or equal to 0.0001. Well, if we're going to look at that, then we know that the remainder, right, is going to be less than or equal to the integral from n to infinity of 1 over x to the 3 halves dx. But I propose that we don't work too hard on this. Let's go back to our work from the last one. The integral from 6 to infinity of that just ended up being 2 over root 6. The integral from 7 to infinity was 2 over root 7. So I think we can safely say that the integral from n to infinity is going to be 2 over the square root of n. So what we know then is that that this guy is always less than or equal to that. So let's set that less than or equal to 0.0001. So I can multiply both sides by square root of n. So 2 less than or equal to 0.0001 square root of n. And then I can divide by 0.0001. I think I said too many zeros there, excuse me. All right, and then 2 divided by 0.0001 is actually going to be 20,000. So what we're saying is that the square root of n has to be bigger than or equal to 20,000. Okay? But, of course, if the square root of n has to be bigger than or equal to 20,000, what is n? Well, n would have to be the square of that, right? So bigger than or equal to the square of 20,000. So if you want that much accuracy, what you're going to have to do is use at least that many terms. 400 million terms. So kind of a lot in this case. So you'll have to maybe think about how important it is that you get this much accuracy in your answer.